Okay, welcome everybody to the last hottest seminar of this spring. So today we have Andreas Nuyts, who will tell us about higher pro arrows toward a model for naturality pretype theory.
Okay, so thank you for the introduction. There's also an introduction to the presentation. So I'll first like to say a few words about why I care about this subject, because I think I come at it from a slightly different angle than many people working on homotopy and directed type theory. So it's not really out of an interest necessarily in directed algebraic topology or synthetic infinity category theory. What I really want is better languages for verified functional programming, because I think functional programs can benefit a lot from being categorically structured. And then if you have native support for that, that would be a good thing. So with native support for relations, morphisms, and isomorphisms, we of course get parametricity theorems for free, as has been known for a long time now. But also, for example, functoriality for free, and not just for type in type, like you get in Haskell with the deriving functor statement, but more generally, naturality for free, and ideally also, if you write, I don't know, some dependent multi-argument function between types that are categories, it would be good if we have a framework and maybe a type checker modality system that can sort out, like, what is this and how do we think about this? Some consequences of the way that I come at this subject are, first of all, that I will stratify types by finite dimensions. So I'm not really interested in the infinite dimensional case, because I think it's not really interested when you're programming. For example, in like functional programmers will be interested in data types. If they're proving stuff, they might be interested in propositions, in sometimes kinds, maybe occasionally a collection of kinds, but usually you wouldn't go much higher. So if you're then a logician and trying to reason about these functional programs, you might want to go up at arbitrary finite dimensions, but I don't really care too much about the infinite dimensional case. Also, I'm not afraid of strict equality. On the contrary, I'm very afraid of burdening programmers with coherence obligations. So I want to avoid that if at all, if whenever possible. And I don't mind as much if my model doesn't present some known form of spaces, but what I want is, if I add features to a language, I want these features to compute so that you can actually reason about your programs and know that the arguments you write will actually say something about the programs you write and their output. And a final thing I should mention is that factorization systems are also not my native language, so this might come up in the question round where I will be noticed to speak more the type theoretic language than the categorical one, perhaps. So first of all, how is directed type theory relevant to verified functional programming? I will illustrate this with an example problem. So we have a category of types, and there you might have a morphism f from A to B. So that's basically just a function between two types. And we have a category of monoids, and as you might know, the list functor will map a type to the free monoid over that type. So we get, if we have a morphism f from A to B, we get a monoid of lists over A, a monoid of lists over B, and then we have this function sometimes called map f. I use the more categorical notation and call it list f, which just applies f to every element. And then maybe we have a morphism, sorry, I'm moving Carlos' image here. We have a morphism between monads from M to N, so a morphism G from M to N. And a monad for a functional programmer means essentially a thing that you can have side effects in. So a program with return value M of A will be a program that returns an A, but performs side effects in M. And what is G is a thing that explains the effects provided by monad M to effects provided by monad N. And then if we have a pair of a monoid and a monad, so we're in a product category, then we can use the writer monad transformer to create a new monad. And the effects that this writer list A M monad provides are all the effects in M, but additionally, it allows to log messages of type list A, and the monoid structure serves to have an empty message and to concatenate messages. But now, if you have a program with effects here, then what you can do is you can decide to translate all the messages to list B. And you can also decide to translate all the effects in M to effects in N. Or you can do it the other order And the question is, will this commute? And I think it's obvious to all of us that this will commute. But this is not obvious to a proof assistant, and that is kind of a problem. Because if you want to prove this and you want to not do half work, but like use proper categorical notions and complete the record types that you use on the way, then this is what you need to do. And so what is written here is not super important. What matters is that it's too much, right? And we can look at a part of it. So if you just want to prove functoriality of the functor list from types to monoids, well, of course you have to give an object action. This is inevitable because, I mean, you have to say what you are planning to do. But then the functorial action, you need to prove, you need to implement this map f function, which is done by recursion, whereas we know intuitively, well, if you construct the list operation, you are basically doing only covariant stuff, so it would be good if this was automatic. Then you have to prove that list f is a monoid morphism. It preserves the empty list, that's trivial, but preservation of the concatenation of lists is proven, again, by induction. And then you have to prove the functor laws, again, by induction. So this is a lot of work, and everything that I've written in red here is things that you would expect should be automatic. If you are in a parametric system, then you can get all the naturality parts for free out of parametricity. But there's still a lot of red in this slide. However, if I specialize my problem a little bit and I assume that f and g happen to be isomorphisms, and I am working in homotopy type theory, then I can invoke univalence and turn all of these things into equality. And then I can do path induction, for example, on this path between A and B, then it becomes a point, this square is then flat, and then it clearly commutes. So then I'm done. So in the case of homotopy type theory, all these red parts are actually for free. So that's a better situation. And what we want here is to also get this for free if your functions that you start from, your morphism that you start from, are not invertible. So that's kind of the sort of thing that I want to provide to people doing verified functional programming. To do that, to have a directed type system that can do this, well, it's more complicated than HoTT, you could say, because you need to keep track of variance. For example, we have this writer monad here. It has, I mean, a monad is more than its carrier, so there are a bunch of operations, but the carrier is just m of a times w, and this is clearly covariant in w, m, and a. And also, it also holds if you consider the structure with it. But if you look at the reader monad, then this is clearly contravariant in the type that it reads from. And then you can look at the return function, which goes from a to writer wm of a. And this is natural with respect to the monoid w, the monad m, and the type a. So what we have here are all just functions. In a dependent type system, you would expect them to live in function types, but they behave quite differently. So we need a system of bookkeeping that keeps track of this. Or we have to find a way to ignore variance. And in homotopy type theory, you can ignore variance because you assume that everything is an isomorphism. But unfortunately, that's not true. Sometimes you have something that's not an isomorphism. And what you can also do is, like Reynolds, drop functions or morphisms and move to relations. But this has a drawback that you forget to compute how to compute a function. Like if you have a function, that function has a graph relation, so you can do a lot with that. But when you move from the function to the graph relation, you kind of forget the computational content. And if you then map a functor over it, you still don't have the computational content. So what we want is a type system where we have preservation of isomorphisms, relations, and also can keep track of actions on morphisms. And in such a system, we could use functoriality or naturality when possible, HoTT when applicable, so when your morphism happens to be invertible, and parametricity as a last resort, you could say, because it always works, but it loses the computational behavior. And so such a system I would call naturality type theory. Right. So before I dive into the details, I want to make a note about vibrancy. And the note is basically that today I do not care about vibrancy, but I will say a bit about it anyway. So a presheaf model of dependent type theory can account for the existence of certain shapes like points, paths, morphisms, bridges. So paths are for homotopy type theory, morphisms for directed, and bridges for parametricity. It can account for unary operations like taking the source of a path or a reflexive path on an object, and for unary equations like saying the source of a reflexive path is the object you started from. But if you want things that are not as simple as what's here, then you typically need some form of vibrancy. Like if you have operations such as composition that are not unary, then you cannot encode that in the base category of your pre-sheaf category, so you need more structure. Or if you want to do something like transport, you need a specific geometry. You need to say we have a path between types and something living in A, and then we can transport it to B. So you need more structure for that. In homotopy type theory, we have Kahn types, which are types where we have composition of paths and transport along paths. In directed type theory, these two things are usually taken apart. So you can have, on one hand, functorial types where you can transport along morphisms between types. And then you have Segal types where you can compose morphisms within types. And then something else you could consider if you have both morphisms and paths, you can ask that invertible morphisms can be promoted to paths. These could be called desk types. In parametricity, what you would want is that homogeneous bridges express equality. And then what equality means well, it depends. If you have also a hot dimension, like in Cavallo and Harper's paper, then you could say, well, homogeneous bridges can be promoted to paths. But if you don't have hot, you can just say, well, homogeneous bridges maybe express strict equality or something. Right. Why is the title of this talk Naturality Pretype Theory? Well, a pretype is a term sometimes used in HoTT to refer to types that are not Kahn, right? And so the plan today is to not look at vibrancy for directed type theory. And I think there are a few good reasons for doing that, for ignoring vibrancy for now. So first of all, it becomes much simpler, of course, but also functoriality and Segal vibrancy are quite brittle if you're using dependent types. So I think if you want a type system with the operations that you're used to, you're going to have to accept that you end up with types that are not Segal and not functorial. So I think it's good to have a system that encompasses all types, including pretypes. And also I think there are promising techniques for actually defining and proving vibrancy of types internally. So there is contextual vibrancy, which has been developed, I think at least used by Boulier and Tabarot in 2017 in the context of cubical homotopy type theory. And I've tried to generalize that in my PhD thesis and then explored an application to Segal types. There's the amazing right adjoint to non-dependent exponentiation by a tiny object, such as an interval in HoTT, by Licata, Orton, Pitts, and Spitters, who use this. Well, they didn't introduce the concept of this functor, but they use it to build internally a universe of Kahn types. And then I've been working on and this has been recently accepted, a dependent version of this. So a type in type theory that is right adjoint to universal quantification over, for example, the interval. And this is useful because it allows you, well, it allows to unify a couple of operations that people have come up with to internalize aspects of pre-sheaf models of type theories. For example, in parametricity, but also in the context of what is it called again, nominal type theory. Like there are a couple of operations, and there was little unifying theory of what these are and how these relate to each other, and the transmission type kind of explains several of them. So this is, I would argue that this is a good way to internalize the fact that you are in a pre-sheaf category. And then there is the internal vibrant replacement monad, where actually I would like to get some feedback maybe. So as an auxiliary definition, I call a category with families locally democratic if basically every arrow in it is essentially a type. So it is isomorphic to some weakening morphism from an extended context. And then what I proved, and I would be interested if anyone knows related results or similar things, or if this was already known, even who knows. So it is well known. Well, you can define dependent type theory as a generalized algebraic theory, and then from the structural rules, from the typing rules, you know what a model is. And it is well known that if you take just the structural rules of type theory, a model is exactly a category with families. And what I've shown is that if you have a category with families, hence a model of dependent type theory, that happens to be locally democratic, then the following two things are essentially the same. On the one hand, defining an algebraic weak factorization system, whose right replacement monad RR preserves pullbacks in a sufficiently strict way that it can be applied to types. And on the other hand, modeling an internal monad RR on types, with a functorial action on dependent functions. So what does that mean? If you have a type T depending on RRA and then a function f from A to T, so you need to substitute by the monads unit to make this work out, then you can apply your functor to this, to the dependent function, and you get something going from RRA to RRT. And to me, this was kind of a surprising result, I think, because the definition of an AWFS looks very symmetric, whereas here the left co-replacement monad is kind of not feasible anymore. It has become this dependent functoriality operation. So I think that's surprising. So if anyone has any ideas about this, I would be interested to hear it, maybe in the question round or maybe by email or something. I would be interested to any form of feedback on this. But I should get back to naturality pretype theory because this was a sidetrack. And there, what we can do is take a model first approach and have a separation of concerns, because we need modalities to track variance. But there is a type system for dealing with modalities, which is MTT, multimodal type theory. And this is parametrized by a mode theory that specifies specific modalities you want. So we can actually instantiate MTT to our setting. And so that's nice because we can say the syntax is their problem and we are just going to instantiate the requirements to build a model of MTT. And similarly, we are going to need intervals for bridges, morphisms, and paths. And these are likely going to be substructural, and that's hard to do in a type system. But we can actually instantiate this type system called the modal transpension system, which has these substructural shapes and then quantifiers to work with these. And again, we can say, well, the syntax for that is we're going to leave that to research on that type system. And also the interaction with MTT, we're going to leave that to work on that. And for now, our concern is just the semantic requirements for instantiating these two systems. So that's kind of the approach that I'm taking. Nevertheless, I want to say a few words about what these systems are, or at least MTT. Maybe I should skip the other one. But so MTT, multimode type theory, is a general system for dealing with modalities. And so let me just sketch the main ideas. So if you have two categories C and D, and you think of them as categories of contexts and substitutions, and you have a functor R between them, then of course you can apply R to the objects, the contexts, and you can apply R to the substitution. So this is kind of the typing rules that you get from this situation. Now, if you assume that C and D are actually categories with families and R is a CWF morphism, then you can additionally apply R to types and to terms. And this is all looking good if you're a category theorist, but if you're trying to implement the type system, this is not good at all, because if you implement a type checker, then for the type checker, the context is not something you can choose. The context is an input. Like the context is just wherever you are, and whatever you've abstracted over, this lives in delta. And then if the user mentions the type RT, then the question is, how do you check this? Because RT is only meaningful in context R gamma, and delta is not necessarily of that form. So the question is, how do we deal with this? And one thing you could do is you could say, well, let's just check T in some context gamma, then RT lives in R gamma, and then just use some substitution from delta to R gamma. So that's the way to fix this. But we don't want to bother the user with asking for a gamma and a sigma, because it's very annoying when you're programming that you suddenly have to specify a context and a substitution. So we want to avoid that. So there should be a universal context and gamma and universal, well, there should be a universal context gamma such that the substitution exists, which means that if there is another such gamma, then we have another morphism. And now gamma and sigma are actually functions of only delta. So I will write them as functions of delta. And then if you add some sensible laws, you see that this is just an adjection. So that's the main idea of MTT, is that whenever you want a modality that can be applied to types, you should have a left adjoint that can be applied to contexts. And this left adjoint is denoted as a log, as you will see in a minute. So MTT is parameterized by a two category called the mode theory. So you have modes, which are, each mode is modeled as an entire category modeling all of dependent type theory, often a pre-sheaf category, but that's not necessary. And then modalities, well, if you have a modality internally, then you can apply it backwards to contexts. So that's really this left adjoint. You can apply it to types. And then if you write a modal type, then the original type is checked in the locked context, because that was the point of this left adjoint. And then the constructor is really the transposition operation of this adjunction that log mu is left adjoint to the modality. How do we model this? Well, for every modality, you need a dependent right adjoint essentially between your mode categories. And we also have coercions between modalities, but let's not dwell on these today. And I wanted to mention briefly that actually a DRA is the same as a right adjoint that happens to be a CWF morphism if your codomain is democratic. Democracy is not a very strong condition, especially if you're working with presheaves and it's automatic. So basically, this means that we care about adjunctions. We need adjunctions to model modalities. As I said, today we only need to instantiate the semantics of MTT. We don't care about the rest. So this is what's important. We need a category for every mode and an adjunction for every modality, essentially. I have also a slide on the model transpension system, but I want to be very brief about this. So the idea is, given some kind of shape, substructural shape, we want a number of substructural quantifiers. If the shape supports weakening, then we can also get, well, the weakening substitution, which also has adjoints. So we get a number of quantifiers. We want to use these, but they are very unusual, very substructural, so that's hard. We don't know how to fix the syntax, so we keep them out of the syntax and we treat them as modalities. But then the problem is they actually bind and depend on variables, which is not supported by MTT. So instead, we put these shape variables like variables of the interval, not in the context, but in the mode. So the mode will be a shape context list in your shape variables. Then I wanted to briefly introduce the semantics of this system, but I think there's no time for that. But the important thing now is that ultimately to model all of this, the main thing you need is just a functor on your base category of your presheaf category. So we can actually forget about the rest and just know that to get some kind of shape, we need this functor on the base categories. So to wrap up this part of the presentation, what we want is to preserve relations, morphisms, and isomorphisms. So we need variance, but we leave that to MTT. We need like intervals, but we can leave that to the model transpension system. We need vibrancy, but this we leave to future work, and hopefully this can be done internally. So for now, what we care about is defining a mode theory, having a presheaf model for each mode, an adjunction for every modality, and then a functor modeling each of these intervals that we need. Right. So this is where we want to go. This is the thing that I want to develop. And I think there are three directions that you can come from it. So we all know what n categories are. There are many ways to define n categories, and one such way is given by Thompson and Simpson's definition, which I will explain later. And this, if you heterogenize, and I will also explain what that means, if you heterogenize Thompson and Simpson's 2 categories, you essentially get pro-arrow equivalence. And so I would argue that there is a part in this diagram missing. So if we do this in a higher dimension or heterogenize this, we should get something. And I think that's a very good place to do directed type theory. We can also come at it from another side. So there is degrees of relatedness, which is basically the relational version of what I want here. So we can try to directify that. And then we also end up here. There's the 2-dimensional version of this, which is an earlier paper. This side has the advantage that it exists as a type system, whereas this side has the advantage, or maybe these 3 things have the advantage that they are known in category theory. So I think it's good to be able to come at this from 2 sides, because here is the understanding of how to do it in a type system, and here is the connection to existing work more. So first of all, these Thompson and Simpson n categories. Let me explain a bit what these are. So maybe I should not explain what a graph and a simplicial set are. So if you have a category, then you can define, if you have a category, you define its nerve, which is a simplicial set, whose nodes are the objects of the category, edges are the morphisms, triangles are the commutative diagrams, and then the higher simplices, they just uniquely exist. There's if you have a boundary, there will be one higher simplex, because we're dealing with a strict 1 category here. And then the question is, when is a simplicial set the nerve of a category? And the answer is when it satisfies the Segal condition, which says that every chain of n edges is the spine or the Hamiltonian path of a unique n simplex. So this means essentially that compositions uniquely exist. And so in this way, we can say categories are basically Segal simplicial sets. Right. Now we can look at n categories, and specifically strict n categories. And here I have the definition of an enriched category. I guess most of you know it. The essence is that your HOMs are not sets, but they live in some given monoidal category V, right? So you have a set of objects, and then for every two objects, you have a HOM thing that lives in V, and then you need it to be monoidal to define the identity and composition. In particular, your V could be Cartesian, and so that we can use to define n categories. So a 0 category is a set, and an n+1 category is a category enriched over n categories. So this is strict. And now we could ask, well, can we understand categories, higher categories, via simplicial sets? So is there some kind of nerve similar to how before we could understand one categories as simplicial sets? And so there is a very nice, very accessible guidebook by Cheng and Lauda, which answered this question positively several times, and then one of these times is via Thompson-Mani and Simpson's approach, which is based on double, and I don't know what the higher word for double is. I use n-fold, so n-fold categories, which I will also introduce here. So a double category is a thing that has objects, horizontal arrows, vertical arrows, and squares, and could be defined or can be defined as a bisimplicial set, so pre-sheaf over delta squared, satisfying the Segal condition in each dimension. If I go to n-fold categories, I need to get rid of the words horizontal and vertical because I only have two of these words, so I will instead use numbers here. And then what a Thompson-Mani and Simpson 2 category is a double category whose vertical arrows are all trivial. So this means that this becomes an equality. So this is basically the same as an object. And here we have the shape that we expect for two cells in a 2 category, right? And so I'm using the horizontal arrows as the 1 cells, the vertical arrows are trivial, and the squares are now the 2 cells of my 2 category. You can do this in a higher dimension, so an n-fold categories and n-simplicial set satisfying the Segal condition in each dimension. And then we can say a Thompson-Mani and Simpson n category is an n-fold category, where only the 1 arrows, 1, 2 squares, 1, 2, 3 cubes, etc. can be non-trivial, so that you are carving out the parts that you need to actually talk about n categories. Again, today I only care about pretypes, so let's forget about the Segal condition and just think about n-fold simplicial sets instead. Yeah, I just wanted to mention that again. Right, so with that, I think I've introduced this part, but not yet how to heterogenize or anything. So let's now move to the pro-arrow equipments or pre-equipments. Right, so what are these? Well, pro-arrow equipment, or simply equipment, is a double category whose horizontal arrows are called arrows and whose vertical arrows are called pro-arrows and denoted with a dash. The dash should actually be vertical, but I can't find a good way to typeset that, so they're slanted for me. And squares, and such that every arrow has kind of graph pro-arrows both ways, and then there are more conditions to be satisfied. And an example is set, where you have as arrows functions, as pro-arrows relations. The identity relation is then equality, and composition of relations is done as it is usually done. And squares are also what you would expect. So you have on the sides 2 functions, f and g, and then what you need to prove to fill a square is that if a and b are related according to R, then their images are related according to S. So this is what you would expect. The example of set is slightly misleading because relations can be flipped, which means that if I have one graph relation, I can derive the other from that and back, which is not possible in a general pro-arrow equipment. So let's instead look at cat, which is also an equipment with, well, the objects are categories, the arrows are functors, the pro-arrows are pro-functors, the identity pro-functor is HOM. Composition is done as for relations, but as existential quantifier, you use a co-end. And then squares are also like for relations, but they are now natural. So if I have, I call this a heterogeneous morphism from A to B along P, then I get a heterogeneous morphism from FA to GB along Q. That's what a square is. But now I can compare this to cat as a Thompson-Mani and Simpson 2 category. So this one has categories as objects, functors as horizontal arrows, trivial vertical arrows, and then the squares are natural transformations. So for all A, you get a morphism from FA to GA. But by the Yoneda lemma, I can equivalently say for all A and B, if I have a morphism from A to B, then I can go from FA to GB. And then I get this kind of square, because this is actually an instance of that. But what we also know is that the identity profunctor is Hom. So this is basically some kind of flat square. So what we see here is that what's different is these ones are trivial, whereas here we have profunctors, but actually the squares are the same thing. So we could heterogenize Thompson-Mani and Simpson 2 categories by dropping the triviality condition. And then essentially we get equivalence is the idea here. So that's what's happening here, right? So you have these two categories, we have pro or equivalence, and if you drop the condition kind of, you end up here. And so I want to do that at a higher dimension. Right. So first of all, why would you care about higher equivalence? Well, we know that the collection of sets, you could regard it as a large set, but we know that you're then forgetting structure. So it's better to look at it as a category, and it's even better to look at it as an equivalent. And similarly for cat, you can say, well, cat is a category, but it's a two category, and it's even more, it's an equivalent. And if you look at equivalent, well, it's an equivalent, but actually it's a two equivalent. What is that? Well, we have objects, which are equivalents. We have arrows, which are equivalent functors. We have pro arrows, which are equivalent pro functors that contain arrows. And then we have pro arrows, which are equivalent pro functors that contain pro arrows, and so on. Right, and so we could define a higher equivalent as an n-fold category with conditions, and we could model that in simplicial sets, well, n-fold simplicial sets, so pre-sheaf over delta to the power n, and maybe we could add morphisms in the base category to get these graph pro arrows out of an arrow. Right, so at this point I have mentioned equivalent pro functors, and you could wonder, well, are you making this up? And I would say only partially, because there are ways to end up in this situation. Like if you look at the Hofmann-Streicher universe, so you have any base category W, you can model dependent type theory in pre-sheaves over W, and then you get the Hofmann-Streicher universe, which is a pre-sheaf over W that classifies your types. Now pick some object in the base category, then we can look at W cells in this Hofmann-Streicher universe, and there are things that contain a notion of dependent W cells for your types in the universe. And additionally, whenever you have some V over W, you also get dependent V cells in your types that are in the universe. But I want to look at this a bit differently, because I think the universe is quite differently from other stuff that lives in this type system. So I want to take actually a fresh copy of W. I say we have W dot, which is again W, but I regard it differently. And for every object W here, I will have an object pro W in W dot, and I will regard the universe as a pre-sheaf over W dot. And why am I doing this? Yeah, so here I would now say a pro W cell is a thing that contains W cells, like a pro arrow is a thing that contains arrows. This is kind of what I'm trying to get at here. And why am I doing this? Because these pro W cells have a completely different meaning. For example, if you're doing parametricity, then you care about discrete types, and you can build the Hofmann-Streicher universe restricted to discrete types. And well, this universe is not discrete. And the reason is that edges in your types, in your discrete types, express heterogeneous equality, but edges in your universe, or pro edges in your universe, are notions of heterogeneous equality. They are relations. So there is no reason to expect this to be the same thing. And similarly, if you're doing directed type theory, you can take the universe of Segal types. It's, well, you might make it Segal, but it's not obviously, or a simple, like it's not Segal in a simple way, I think. And the reason is that arrows in Segal types express morphisms, but pro arrows in U, they express pro functors. They are things that contain arrows. And similarly, triangles in Segal types express commutativity, but pro triangles in this universe, they are notions of commutativity. So they are like predicates on boundaries of triangles. So that's quite different. So I like to distinguish between that, because then you can actually start adding stuff to this. So this Hofmann-Streicher universe, it's not just a type internal to presheaves over W dot, it's actually a category internal to that. Because there are not just types, there are also functions between types. And a category in particular has a nerve, so the universe is a simplicial set. And a simplicial set internal to presheaves can be regarded as a presheaf over the product with delta. So you could say this adds a directed layer on top of your favorite type theory, at least your favorite presheaf type theory. This is not properly developed or anything. This is just a way of thinking that I'm explaining here. But in particular, you could iterate this idea, and you could start from sets, which are basically presheaves over the terminal category. And then you could take the universe of that, which would be a presheaf over top dot times delta, but let's ignore top dot because that's the terminal object. And so what I'm saying here is the universe of sets is a category or a simplicial set. But now what happens if I look at the universe of simplicial sets? Well, it lives in this thing dotted times delta. So it's kind of an equipment because it has arrows, which are functions, and it has pro arrows. And then you could take the universe of that, which now lives in delta dot dot times delta dot times delta. So you have arrows and pro arrows and pro arrows. So this kind of arises somewhat naturally. So I think these two equipments and higher equipments are really relevant things to look at. While I'm at it, I wanted to kind of argue against focusing too much on self-classification. So I wanted to say, by nature, classifiers typically don't contain themselves. Like, for example, I mean, these are not mathematical examples, but all of mankind is not an example of a human, and all the world's literature is not an example of a book. And forcing things to be otherwise is a priori unreasonable. And like, there are special cases, like if you are classifying collection-like objects, then you're in a somewhat better situation. For example, the collection of sets can be regarded as a set, but there is more structure, or the collection of categories can be regarded as a category, but there is more structure. And it's not because you can truncate these things to achieve self-classification, to give them the same structure as the things that they contain, that this is necessarily a good idea. And when developing a language, I would advocate to provide the user with both the unscathed classifier and the truncation modality, so that the user can truncate if they want to do that, but not if they don't. And this can be done with a multimode type theory, where a priori your universe lives elsewhere than the types that it classifies, but maybe you can truncate it back to that same mode. Yeah, and then for people who actually are fans of self-classification, I know that there are fixed points, like the collection of n groupoids is an n+1 groupoid, and this is a fixed point at infinity. So, I mean, there's nothing against this, but I'm just saying not everything should be this situation. And I think we are this is sometimes overlooked, in my opinion. So I wanted to say that. And while I'm ranting, I wanted to also advocate against the Grothendieck construction, or at least against seeing it as the sigma type for categories. So let's first look at what the Grothendieck construction is. So given a category C and a functor C from D from C to cat, we can build the Grothendieck construction. The objects are basically just the sigma type of objects, so a C in C and a D above it. And the morphisms are, well, a morphism from C1 to C2. And then here I want to say a morphism from D1 to D2, but they live in different categories. But fortunately, D of gamma gives me a functor, so I can transport D1 to the side of to where D2 lives, and then I can consider a morphism there. So that's what the Grothendieck construction does. But if you look at cat as a cat, then you're actually truncating it. So let's make that explicit. We have a functor arrows from equipments to categories that discards the pro arrows and keeps the arrows. And what you're doing here is you're considering a functor from C to the arrows category of the equipment cat. And this thing has a left adjoint, which turns a category into an equipment by freely adding these graph pro arrows. And so we could use this junction to say, well, equivalently, we have an equipment functor H from C with free pro arrows to cat. And so now we could ask, well, can we generalize this away from this specific category, from this specific equipment to a general equipment E? So let's see what we can do with that. Given an equipment E and an equipment functor H from E to cat, let's try to build some sigma thing. So as objects, again, we take C in E and D above it. as morphisms, I take a morphism in C, and then I look, what does H give me for that? And H of gamma is a functor, and a functor contains a relation, you could say, but this is the relation maps to. And I don't want to put a morphism here, because then actually I'm looking at a graph pro functor for this functor that I get here. So I want to use the original thing, and I'm going to say D1 immediately strictly maps to D2. And this is the same that you're doing in the category of elements. So you could call this the equipment of elements. And then for pro arrows, we're going to say we have a pro arrow in C, and then H of that pro arrow is a pro functor in cat. So we can look at heterogeneous morphisms along that pro functor. And that's what we're going to put in the second component. So this might look a bit arbitrary, but first of all, this is essentially, so I'm ignoring composition of pro functors here, but this is essentially the category of elements internal to presheaves, internal to simplicial sets. And also this is what you need, for example, if you want the equipment of pointed categories or something like that, then you get basically a sigma type of this form. And you can actually retrieve the Grothendieck construction from this. So if we have an E and an H, we can do this construction. There is a first projection to E, and I'm now instantiating E with C with 3 pro arrows. So I get this, and then I can apply to this a functor that turns equipments back into categories by discarding the arrows and keeping the pro arrows. So what I have now is here, I have the pro arrows of this thing. Here, I have taken C, freely added pro arrows, and then removed the arrows. So basically, I have zigzags in C now. And then, well, if I have a morphism, then certainly I have zigzag, and then I can define the Grothendieck construction as a strict pullback here, because what this is a morphism in C, which gives me a pro arrow, and then above that pro arrow, I have a morphism in D, and so all of that together is a morphism in the Grothendieck construction. So to me, this thing is more natural. I'm okay if you disagree with me, but at least I would hope that you acknowledge that there are other sigma-like constructions for categories. And so I think that means that when developing a directed type theory, it's probably not a good idea to say when there is a sigma type somewhere to immediately say this is going to be a Grothendieck construction. I think there is much more wealth in the sigma type world for directed type theory. So that's the point I wanted to make here, basically. Now I am far behind. That's not good.
Well, sorry, if I can ask a question on that slide. So you mentioned what was the example you gave, like a pointed categories? Yeah. So how do you instantiate, like, what are H and E?
Okay, so
for that case?
E is cat and H is the identity, basically. So an object is a category and an object of that category. A morphism is a functor, and then it should preserve the chosen object. And a pro arrow is a pro functor, such that, well, a pointed pro functor, basically, which corresponds to the pointing of the categories.
Okay, and that didn't work in the original case, or sorry, yeah, I know it's
so here, if you do the same thing, first of all, is it well typed? So we have, for C we take cat, but we need a one category here. Yeah, so you cannot end up with a two category to begin with. So you're kind of.
Oh, okay, right. I see. You want the two category. Okay, sure.
Yeah, I just want don't want to lose any structure anywhere. That's kind of the guiding principle.
Yeah, I see. Okay. Thanks. Yeah.
Right. So I got sidetracked a bit again, but basically I had explained like how I'm viewing pro arrows in a higher dimensional or thinking about heterogenizing these n categories. Now I want to talk a bit about this one. Let's see if there's time for that. So yeah, so the idea here is degrees of relatedness is basically the relational version of what naturality type theory intends to be. It might be a bit alienating because on the one hand, it goes beyond Reynolds parametricity, and on the other hand, it's much less than higher category theory. So it's somewhere an intermediate point between places where many people are working, and it's like maybe a strange place to be. But it does explain a couple of known relational modalities, and also it has the virtue of existence as a type system, unlike most directed things. Right. So what is it? Parametricity is about relations. So we'll equip types with proof relevant relations. But what's unusual is that we take multiple relations and we index them by a degree I. And so the plan is to take just one relation for small types, which expresses heterogeneous equality, but more relations for larger types. And this is analogous to what we have in these higher equipments. And the proofs are called I edges. And the idea is that a I+1 edge is kind of a pro-I edge. So it contains I edges. We will describe function behavior by saying how functions influence the degree of relatedness. And this framework kind of gives a semantics, well, not kind of, it gives a semantics for parametricity, ad hoc polymorphism, irrelevance, shape irrelevance that pops up in Agda, and some aspects of algebra, etc. And the system is governed by 4 laws, you could say. The first one is reflexivity. So all these I edge relations are reflexive. You could also say if A equals B, then A is I related to B. I'm not distinguishing between propositional and definitional equality here because I'm in the semantics. And it's a strict system, no homotopy here. The second law is degradation. So if stuff is I related, then it's also I+1 related. The third one is dependency. So if I'm saying that stuff is I related heterogeneously, then I need to say this along some I+1 edge. So this again expresses that these I+1 edges are like the pro-I edges. They contain the I edges. And then there's identity extension, which corresponds to discreteness. So homogeneous zero relatedness expresses equality. So in other words, heterogeneous zero relatedness can be understood as heterogeneous equality. I'll come back to this in the directed case, so we will see this again. Don't worry. Just to understand what this means a bit, and then this slide, I think, will also make more sense in the directed version. But we can say we have homogeneous zero relatedness, which expresses equality. We have heterogeneous zero relatedness, which expresses equality along some R. And this R is going to be a one edge between types, and it's going to be just any relation. And then we can have one edges in a different type than the universe, for example, in type of groups. These will be algebraic relations, so group relations respecting the group operations. We can also look at heterogeneous one edges. These live along some two edge, and this two edge could, for example, go from group to monoid and specify that your one edges should be relations respecting E and star. But actually, V could specify that Q should be anything, so it's just something. How can we use this to understand modalities? Well, let's look at the if operation, which is parametric. So it takes a type X and it gives you an element of Bx, which is bool to X to X to X. B is a function from the universe to itself, and if is a parametric function. This zero here means that I am at the mode of types that have 0 + 1 degrees of relatedness. So this universe classifies the types with 1 degree of relatedness, and it has 2 degrees itself. So what happens here is we have this universe which has 2 degrees, and then we go to Bx, which has only 1 degree. And what parametricity means is if you pick a relation between X and Y, then the outputs will be heterogeneously equal according to this relation. And so this BR will be, well, we have B from the universe to the universe. So here we have 2 relations on both sides. And for this to be well typed, we need BR to be a one edge. So again, a relation between Bx and By. And then this one expresses equality. So we also assume that equality is preserved. And so we get 2 diagrams here. And these basically express what these modalities mean. So a parametric function from level 1 to level 0 is something that satisfies this behavior, and a continuous function is one that satisfies this behavior. And it is required that the codomain of a parametric function is continuous. This is kind of how the modalities work. Right, so what is the mode theory here? Well, the modes are, I call them depths. So basically they are the number of relations you have -1. There is no good reason in hindsight for the offset. The modalities from P to Q basically answer the question, if I want I-related outputs, what do I need for my inputs? So a modality from P to Q will give you, for every degree in the output type, will give you a degree in the input type, or maybe top if it wants always relatedness, or equality if it's not requiring anything, right? So it's a function that goes the other way, kind of. And then in model, and so we're mapping I.mu related inputs to I related outputs, and in model types, stuff is I related if it was I.mu related in the original type. So that's the idea. Two cells are degree-wise inequalities, and depth P is modeled in cubical sets with P+1 different dimension flavors. So P+1 different intervals, and corresponding to this degradation law, there are injections from one interval to another. So that explains this thing, and now the question is, how can we directify this? And so we're going to instead equip types with, again, multiple proof relevant relations. We now call them, I call them IJets, because what they intend to be is pro to some power arrows, but that's a really annoying word, so I call it IJets. And so these are indexed by a degree I, and we'll describe function behavior by saying how functions influence the degree, but also the orientation of jets, so that we can be co or contravariant at every degree. Right, so these were the laws for degrees of relatedness. The last one concerns discreteness, so it's about fibrancy, so let's ignore that. And so we get three laws in the directed case: reflexivity of the jet relation, which is just the same as here. And then the degradation law turns into this graph pro-arrow law. The jargon in equipment language is companions and conjoints. So if I have an I-jet from A to B, I get an I+1 jet both ways. So I get a pro I-jet both ways. And then dependency is still the same. So an I-jet from A to B requires an I+1 jet between the types. So a morphism requires a pro functor, for example. So how can we understand this in the directed case? The zero jets express still some form of equality, but now it's along a functor. So now this says A maps to B along F. And then F is a one jet, which is a function between types. But I can also look at the one jets between groups, and then that will be a group morphism, ideally. I can more generally look at heterogeneous morphisms, which will be along a two jet. And a two jet in the universe will be a pro functor. It could be one of the graph pro functors of the forgetful functor from groups to monoids, for example. So this is kind of how the jet relations are intended. How can we build modalities for this? Well, suppose we have a functor from groups to types, which basically just takes the carrier, and then we can take the limit of that functor. A functor is a diagram, so you can take the limit, and we can actually express this using modalities. So here, if two groups are equal, then their neutral elements are equal. And if you have a group homomorphism, then the neutral object of G will map to the neutral object of H. And this mapping to is along the underlying function of the morphism. So what happens here in the domain is, well, if you have a morphism of groups, you get a morphism of types, and this morphism is the one we need here to express the mapping relation. And then this one expresses some form of equality, so we just keep that one, and this way you get a modality for taking covariant limits of covariant functors. Similarly, we can look at a contravariant situation, but maybe I should skip this a bit. But basically what happens here is you turn around one of the arrows. That's kind of the idea, so that's an option. And so what's the mode theory? So we will say modes are, again, dimensions, so numbers of jet relations. And here, so I won't come back to this in this presentation, but actually there is the option to mark any degree as either symmetric or directed. So, but let's ignore that and let's assume that modes are numbers. And then modalities from P to Q, they still answer the function, if we want I-relatedness in the codomain, what do we need in the domain? So they assign to every degree of the codomain a degree in the domain, but also an orientation. You could ask the morphism to point forward or backward or both or either. And so we say that there is an I-jet in the codomain if there is an I.mu jet of the required orientation in the domain. And the situation in model types is similar. So there is an ijet in the model type if there is an ijet mu jet in the original type. And twistles are still degree-wise inequalities. Right, so this is all pretty fast, but this way we can kind of rectify these degrees of relatedness, and we end up in this place essentially. So I think I have time to say some things about the model, because my last few slides are rather empty. So first of all, the simplex category is a skeleton of the category of finite linear orders. And that's good to know because it's easier to define operations here because simplices are kind of small. I don't know, they're hard to manipulate somehow. So Pignot and Krauss define the twisted prism functor. They don't actually define it on this category, but you could easily do it. So you get an order here, you duplicate it, you take the opposite of one, you take the union of both, then it's no longer linear, but then you say, well, everything on the left is less than everything on the right. So what happens is if you have, for example, A is less than B, then you get B0 is less than A0 because here we're on the upside, and then both of these are less than the other side where the arrow still points forward. So that's what the twisted prism functor does. And I think this is a good thing to reconcile the view of Hom on one hand as a co- and contravariant bifunctor, and on the other hand as a constrained function type like the path type in HoTT, because viewing it as a path type means that you can apply it to 0 and 1, but then somehow one application should be contravariant and the other should be covariant. And I think this functor captures that nicely by taking the opposite at the source side. So the twisted interval is actually better behaved as a shape on the twisted cube category, which is the one that actually Pignot and Krauss use. And this is roughly the subcategory of finite linear orders, or of delta, generated by the terminal object and this twisted prism functor. So we will use twisted cubes instead of simplices. And actually, and this is relevant to the next slide, Pignot and Krauss carved the twisted cubes out of the graph category and not out of the linear order category. And so how do we do this? Do a similar thing for these higher equipments? Well, I define a jet set as a set equipped with n different prop-valued jet relations, which are reflexive and such that this is like the companion and conjoint thing, the graph grows out of an arrow. So an I jet in one direction implies an I+1 jet in both directions. We can easily define intervals. So basically you have two elements and then there is an I jet between them so that there are also I+1 and I+2 jets pointing both ways as a consequence of this. And then we can define twisted prism functors for these jet sets. So there is, for every degree, there is such a functor which only opts that degree and leaves the other degrees alone. And then we can say, well, jet cubes are generated by these twisted prism functors. But then the question is, what is a morphism of jet cubes? Because Pignot and Krauss don't use all morphisms, they select some, and their selection is hard to generalize. So here's what I did. So I've defined the objects of jet cubes, but not yet the morphisms. But a jet cube is in particular a jet set. This is a category, and I can forget the relations, and I get a set. What I did is I introduced a cube category here with two parameters. The first one says, what interval operations do you want? So basically, I say the cube category is essentially the opposite of the Kleisli category of that monad. So that means a cube morphism here will substitute every dimension of the codomain with an expression over the domain using the operations provided by M. And then the second parameter says whether you want diagonals. And then a cube gives rise to a set of its vertices, of its endpoints. And this corresponds to what's happening here, because the way we define the twisted prism functor, it actually always multiplies with a jet set on a two-element thing. So basically, if you go from here to here, you're also taking the corners. And we can add a function here that forgets the degrees and forgets the orientations and just gives you a cube. So what we have here are three categories and functors, and here we have a set and two maps, and I want to turn this into a category, and what I can do is take a pullback and say this should be fully faithful, and that defines what are my morphisms here. So that means that a morphism of jet cubes is a morphism of cubes such that the corresponding function on endpoints respects the I-jet relations. And then I looked at how we can instantiate M and this Wazy cube. And it turns out that there are only two instantiations that seem really interesting. One is where you provide the operations 0, 1, and evolution, and in the other, you provide also connections and then the law of excluded middle. So it's Boolean algebras and not the Morgan algebras.
And does square mean, does that mean yes diagonals or no diagonals?
No diagonals, no diagonals.
Yeah.
Yeah. So this is kind of a fine situation. Yeah. And then the question is, when is a morphism? I can't read. There's this Zoom thing in front of it, so I don't know what exactly I wrote. But when is a morphism of cubes? Morphism of jet cubes? So this question turned out to be hard, and I developed a calculus to figure that out. And this calculus was also pretty tough to prove sound and complete, because I mean, it ended up being ugly combinatorics. Maybe there is a more fundamental treatment hiding there, but I didn't find it yet. And then so I've talked about the semantic modes, then there need to be semantic modalities. These are still in progress. So I think I've discussed everything in this diagram. This is the bibliography, and so that's what I had to tell. And I see that I am extremely punctual. So
yeah, perfect
nice.
timing.
Yeah.
So yeah, well, thank you. Let's all visually applaud for the speaker.
I will try to expand. Yes, nice.
All right, great. Then anyone feel free to ask a question. Just unmute yourself. So I guess I'll start. So, so I mean, at the very beginning of the talk, you were talking about, you know, some things are going to be from, you know, the base category, and some things are going to be fibrancy conditions.
Yes. Yeah.
But it seems like you have an awful lot that's in the that's kind of built into the theory, right? Including things like variance and stuff are built in, right?
Yes. Yeah.
So then what actually gets added in the fibrancy?
But so I think I build in variance, but in only part of it. So in HoTT you would express the availability of a transport operation by saying, if you have a path between types A and B and you have something in A, then you get something in B. So in directed type theory, this would be if you have a morphism from A to B and you have something in A, you get something in B. But the variance that I'm dealing with in the modal system just tells you what direction the arrow between A and B is going to point, but it doesn't give you the transport yet. So if you have like a covariant type in the modal sense, that just tells you the direction of the arrows, but it doesn't tell you that you have like a functor on type set or anything. So that you also need your type to be like a fibration, or I don't know if people call this, I guess fibrant is the word, like a covariant fibration. So you need both things. Like one is for keeping track of the direction of the arrows, whether they flip or not, and the other is for actually doing the transport. And so I'm deferring that to future work.
Okay, but I guess then what you are handling is like that some particular operation might, you know, flip the direction of arrows, yes, or something, yes, exactly. Right? But you just don't, you're not, oh, okay, I see. Yeah. Anyone else have a question? I can keep going.
Yeah, I also crammed a lot of content in this thing, I think, in hindsight. So if there's just anything that was unclear or something, you can also ask about it.
Well, there's a couple things there. So just very near to the end, you said something about Hom, thinking of Hom as a constrained function type. Yes. I guess, what did you mean, like functions satisfying some? Yeah, right here, like
condition on 0 and 1. Yeah, yeah.
What do you mean on 0 and 1?
So like in cubical HoTT, you would say a path from A to B is a function from the interval to wherever A and B live, such that at 0 you get A and at 1 you get B.
Sure, okay.
And so it would be good to have that in directed type theory. But then if you're looking at morphisms as functions from the interval, then you can apply them to 0 and to 1. But getting the source of a morphism or getting the target, like if you think of the total space as kind of the twisted arrow category, then that's a different variance. So that's a very strange situation where first of all, it's strange that function application has a non-trivial modality with respect to the function that you're applying. But here, that modality even depends on the argument, which is entirely bizarre. But I think the twisted prism functor wraps that exactly. So I think that's what we need somehow.
Okay. So again, I guess going back to how you started the talk, I guess to be controversial, another thing you might want instead. So you talked about like things like parametricity, for example, but even for univalence, you can think of this as something that by default holds externally but not internally. Right, or could hold. I mean, maybe I should say like, right. There's nothing you can do in the syntax that specifically violates it, but neither is it actually provable internally without
like you can have a language satisfying that property.
Right. So, and for some of these things, I wonder. So the difference between having univalence or internal parametricity and not having it is that for any specific, for any closed construction in type theory, right, then there should be some way to derive the parametricity statement, but not for an arbitrary type or not for, some neutral terms. So, I mean, I wonder what's your opinion? I mean, this is something, I've certainly thought about too, but your opinion about like, at what point is it worth it just having, you could imagine just having some, tactics or reflection-based system that just tries to crank out for any, for list as defined, crank out all of the red text from your slide, but not having it generically in all, things like U to U.
So I think I'm increasingly thinking that if the support for that sort of thing is very good, then it's not so distant from a system where you actually have it internally.
Well, except that you don't. I mean, there is a difference in the like what's true for
definitely,
but
I think the difference is mainly like so for closed things you get the result either way. For open things, you only get it with proper internal support and not with some sort of translation. But then you could just say, well, if you are interested in univalence or parametricity or whatever, you can always, I mean, the open translation will also, or the parametric translation or univalent translation will also translate the context and just add additional variables. And I think if your language support is maybe good for that, then these variables can be kept from bothering the user too much. So in this sense, I hope that it's possible to give the user the impression that they are not actually in that situation, even though they are. But I think if you look at work on parametricity and even these univalence translations by, I think, is it Tabarot? I think there is a lot of commonality in the insights needed either way. So I think, I mean, I'm definitely interested in that. I cannot say right now which is the better approach, but I think there is much transfer of insights possible between both ways.
Right. And especially as it gets increasingly complex to bolt these things in.
Yes,
right.
Yeah, so that is one concern, of course, that the system might end up being very complicated, and then it would be good to kind of be able to tear it apart again and maybe understand these parts as translations or something. That would be interesting. Yeah.
Right. But I guess one thing I wonder is, is it, and it's very complex in appearance, like in full generality, but for some specific thing, do you have any sense of like, maybe if you're just talking about some particular term, like maybe all the obligations are not so bad. And like in cubicle type theory, sometimes people are scared of, the definition of HCOM, but then if you look at a HCOM, it's like not so,
Yeah.
right?
So even because now you're looking at a specific function, but I think even in practice, programmers will typically be at the lower level, so they will be dealing essentially with sets and categories, and very occasionally a two category or something.
Right.
And so, like in the case of degrees of relatedness, yeah, maybe. Well, I can go to the slide. It's not super important. What we saw is that you have a bunch of modalities. No, this is not working. Here, I guess. Is that you have a bunch of modalities. There's this pretty complex system, but if you now say like P and Q are both at most one or something,
Right.
then it turned out that all modalities that you get, or maybe all but one, actually already had a name in existing literature. So basically what that means is you've developed a general system at that point that gives you a story for all these things that have already been observed. So I hope somewhat that this is also the case maybe for the directed version.
Right. Yeah. Okay. Yeah. I mean, that would be my hope as well. Yeah. I mean, in any case, it will certainly be a lot simpler than the general case for looking. Yeah.
That is for sure.
Yeah. Well, does anyone else have any question?
There is a red bullet here, but I think someone posted in the slides are
yeah. Okay. No, that was
thanks for that.
Yeah. Okay, well then I guess let's thank the speaker again.
Thanks for inviting me.